Okay, so next we'll have Partha Sambasivan from Virginia Tech, who will tell us about TEPID-ADAPT, adaptive variational thermal state preparation at low temperatures.
Thank you. So hi, my name is Bharat. I'm a postdoc at Virginia Tech with the Barnes Economo Group. And today I'm going to talk about recent work of ours that's on the archive now, where we propose a new method for thermal state preparation at low temperatures. So throughout this conference, you've heard that state preparation is a crucial subroutine for many quantum algorithms, so I won't go into it further. But existing methods that we have currently primarily focus on ground state preparation. The type of states we are interested in this work are low-lying eigenstates of a given Hamiltonian and the corresponding low-temperature Gibbs states of that Hamiltonian, where the Gibbs state is defined as the following way, and it describes a system that is held at equilibrium with a thermal bath at temperature T. The Gibbs state uniquely minimizes the Helmholtz free energy, where S here is the von Neumann entropy, which is a quantity that is notoriously difficult to measure on quantum devices, which requires some sort of partial tomography at least to do. The tool we'll be using in this work is ADAPT VQE. So the usual variational quantum eigensolver has a classical quantum hybrid feedback loop, where on the quantum computer you evolve your state by your ansatz, and then you measure the cost function, and then the optimization takes place on the classical side. In ADAPT VQE, there is an outer loop where the ansatz itself is built iteratively, based on information you have about local gradients of the cost function. Here I show you a small cartoon of what the ansatz would look like after the third adaptive iteration. So our method is called TEPID-ADAPT, where TEPID stands for truncated eigenvalue parametrized initial density. The motivation is that at low temperatures or large beta, only low-lying eigenstates of the Hamiltonian contribute significantly to the Gibbs state. So you can imagine doing a truncation of your spectral decomposition where you've cut off the sum at some finite value m, which is less than 2 to the n. Here, the psi case and e case are the eigenstates and eigenenergies, respectively. So now let's consider the following state, which is diagonal in the computational basis. So here, C case are the computational basis elements, and I've just replaced the psi case with C case here. So the claim is there exists a unitary V that can map you from this state to the Gibbs state. Now let's do the same truncation here as well, where you truncate the sum at some value m. Now the claim is there exists a unitary V that takes you approximately from this truncated state to the Gibbs state. And this is a good approximation when the temperature is low. But we still don't know what the energies are, so let's do the best we can and write down a parametrized density matrix that's diagonal in the computational basis that has support only on m computational basis states. And these variational parameters will optimize and hopefully drive them to the correct Boltzmann weights. So the broad block diagram of our method looks like this. So UM is a unitary that uses some ancillary qubits to prepare that diagonal density matrix I showed you in the last slide on the system register. And then you have an adaptively generated unitary purely on the system register that rotates you from the diagonal density matrix to the Gibbs state approximately. Notice that at a particular instance of the ansatz, the von Neumann entropy does not change beyond this point because I'm only doing operations on the system register. In other words, entropy is invariant under unitary transformation, so you don't need to worry about the changing entropy after this point. So this leads to a nice breaking up of the free energy itself. So the energy part of the free energy depends on both sets of parameters, mu and theta. But the entropy itself depends on only the mu set of parameters and has no dependence on the theta set of parameters. And since rho m is a diagonal density matrix in the computational basis, the von Neumann entropy is simply just the Shannon entropy. And you don't need a quantum computer to measure this, you can just simply write it down so there's no classical or quantum overhead. So I want to emphasize here that at every VQE subroutine, all the parameters are optimized. So you're allowed to change mu and theta at every single VQE subroutine. So let's look at some nice properties of this method. Let's assume that VA of theta star is the converged adaptively generated unitary for some temperature beta bar, some inverse temperature beta bar. Recall that this quantity just rotates you from the computational basis to the truncated eigenbasis. So it's a basis change unitary. So to get access to the excited states or low-lying eigenstates, all I have to do is prepare the corresponding computational basis state and then act upon it with VA, the converged VA, and I get the eigenstates out. So here I show an example where, let's say, one of your computational basis elements is that quantity, and then you can just prepare this and then hit VA and you have the second eigenstate. To measure the energies, so well, the energy gaps you get for free because you can just take ratios of your mu parameters and you just get the energy gaps. And all you have to do is measure one energy and then you get the full eigenspectrum. Full truncated eigenspectrum, I mean. So yeah, access to excited states comes completely for free through preparing the Gibbs state at low temperature. We also have access to Gibbs states at lower temperature. So let's say you take beta to be greater than beta bar, where you've already prepared the Gibbs state. The excited states become increasingly less important when I lower the temperature. So you can use the same adaptively generated basis change unitary without any parameter reoptimization to prepare Gibbs states for lower temperature with increased fidelity. And the increased fidelity is because of this statement right here. All you have to do is appropriately change the initial state. So this step of the unitary will have different parameters, mu prime, where beta is the new temperature that you want to prepare the Gibbs state for. This is valuable because as I increase beta, this second part of the free energy becomes small, and so it becomes numerically difficult for the optimization to accurately prepare the Gibbs state. So you can use this method to prepare it at a higher temperature and then just cool down like this. Okay, so let's look at some results. So the x-axis of this plot, so very broadly speaking, these two plots show the two features that I talked about. So the first one's going to show you the excited states, this one's going to show you the lower temperature Gibbs states. So the x-axis here is the state index. So all the numbered indices correspond to the low-lying states. So 0 would be the ground state, 3 would be the third excited state, and this would be the Gibbs state. On the left axis, I'll plot the infidelity. So for that, you'll be looking at the circle markers. And on the right axis, I'll plot the relative error. So for the first 5 quantities here, it's going to be the relative error in energy. And for the Gibbs state, it's going to be the relative error in free energy. And here I've shown a schematic of what the spectrum looks like for this model that we've considered, the Heisenberg XXZ model in the antiferromagnetic phase. And we've taken 6 qubits and the inverse temperature is 3. So when you have only 2 states, when you've truncated up to just keeping 2 states, that's what the results look like. The eigenstates are prepared very accurately, and that's the quality of the Gibbs state preparation, and these are the 2 states that he's kept. And then that's what it looks like for m equals 3. You see an improvement as expected. Same for m equals 4. And then for m equals 5, it actually misses preparing the last excited state, but then you see that the thermal state still has very high quality. So this means that at this temperature, this state is not very important for the thermal state itself. Now let's move on to the right plot. So the x-axis is the inverse temperature. So higher beta is lower temperature. And on the y-axis, I'm plotting the relative free energy error of the Gibbs state, of the prepared Gibbs state, with exact diagonalization. So here, I plot the results for m equals 2. So the circle markers indicate where we have done our VQA to prepare the Gibbs state. And then at beta equals 3, we stop doing that, and then use the same ansatz to extend the Gibbs state to larger beta. And we see that the fidelity keeps dropping. Same for m equals 3, m equals 4, and m equals 5. Okay, so as a summary, I'll just put up this workflow of our method, where the inputs are the Hamiltonian, the target inverse temperature, a computational subspace which has m elements, some pool operators that you use to adaptively build your basis change ansatz, and then you do the usual sort of adapt optimization over here. And the output you get out of this is the Gibbs state at the target temperature, the low-lying eigenstates that contribute to the Gibbs state significantly, and then also the Gibbs state at any lower temperature. And with that, I'll thank my wonderful collaborators and the audience for your attention. Thank you.